I will not be reading the whole question in the interest of time, so you can pause and you can read and understand the question first. I directly go into the solution to that, so we should be aware of the background. The background is when it's important to understand how the current rises in a conductor. So if we have time on the x-axis and we have current on the y-axis, and if a DC voltage is applied, for example, to the Q31 circuit, the current will start from 0, it will grow exponentially, and then it will become a constant value. So not a perfect graph, but good to understand. And let's say that the constant value or the steady value of the current is I. So it takes some time. So let's say from point O to P. This is from O to P. P represents the time at which the current becomes steady. And therefore, the response to this question has to be in two parts. Part 1 will be O to P, and part 2 will be P to Q. So let's analyze the response for both the cards. So I call it as card 1 and card 2. And before we go into that, let's do some naming. This is our switch, and the two ends of the solenoid in card 1 are A and B respectively, and in card 2 are C and D respectively. So right now we are focusing only on the path O to P. So when the current is rising, it increases from 0 to a finite value, constant steady value. So as far as current is concerned, we know this above is the graph. So current will be starting from 0 and increasing exponentially. So the graph remains the same. I will not go into the detail. So it is the same. And what happens because of the increasing current? So there will be a magnetic field introduced in the coil AB. But before that, just one recap that in case of a inductor, there is always a back EMF introduced as soon as there is a change of current. So there will be a change of flux, and therefore the circuit will try to induce a back EMF, or it will try to induce a EMF in such a way that it will oppose the main EMF, which is E over here. So, and as a result of that, the current takes there is a lag, and that lag is represented by the part of the graph which is OP. So you should be aware of that background. All right. And what happens to right now we focus on the card C1. So what happens to B, magnetic field? So magnetic field is directly proportional to the current. Magnetic field inside a solenoid is directly proportional to the current. So it will also follow the same path. It will start from 0 and it will go to a maximum value. And then what happens to the flux? So you remember phi is given as B dot A, which is a BA cos theta. So from this expression, we know that phi is directly proportional to B. Therefore, the flux will also increase in a similar fashion. So 0 to a steady value for this observation will be there for current, magnetic field intensity, and also for the flux. So as far as the galvanometer deflection is concerned, so G1 galvanometer. Galvanometer does two things. It shows the direction of the flow of current in the circuit, and depending on the deflection, we can also see how strong the current is. So it gives an idea about the magnitude of the current also, not the quantization. It doesn't tell how many amperes flow, but it can give a direction, and a strong deflection means a strong current. So in this case, as soon as the switch S is closed, so we have the positive side of the battery and negative. So current in the external circuit always flows from positive terminal to the negative terminal. So there it is. Now if you see the deflection, there is no doubt that the deflection in the galvanometer will be, maybe I can write here, towards right. Yeah. And it will be a deflection starting from 0, and as the current reaches the peak, it will be, the maximum deflection will be at the peak, which is point P. Now if you observe very carefully over here, so the direction of current enters into the coil like this, and then current moves like this. If there is a person looking into this circuit from this direction, looking into the solenoid or cart 1, so the direction of the current is clockwise or anti-clockwise? So it is clockwise. So, and a clockwise direction of the current signifies that it is going to be behaving like a south pole. So that's the south pole, and obviously the other side will be the north pole. So that will be the polarity of the magnet. So whenever we have a DC voltage applied across an inductor, that inductor or that solenoid will behave like an electromagnet, and that's how it is behaving right now. Yeah. Now let's see the response in the card 2. So as soon as there is a increase of current, there will in the cart 1, this will be followed by increase. Maybe I can as soon as the magnetic field before that, let me draw the direction of the magnetic field lines as well. So outside the magnet, the magnetic field lines go from north to south, and inside from south to north. So same thing in the downward direction also. So when the current increases from 0 to maximum steady value, there will be a flux introduced in the cart 2 as well. And this flux will be introduced in such a way that it will try to oppose the very phenomena that caused the occurrence of this flux in the cart 2. So which essentially means that this side C of cart 2 will essentially behave as a south pole, and obviously the other side will behave as a north pole. Yeah. So if you see the magnetic field lines in the solenoid in cart 2, they will be like this. Apply the same logic. All right. So the current, yes, it will also try to. So what is happening is that we have to determine the direction of the current. So if you look from left to right towards the cart 2, it is behaving like a south pole, and south pole means the current will flow clockwise. Yeah. So if the current has to flow clockwise, then the direction will be this, which means it will be this direction, yeah, and like this. So as far as the direction of the current, maybe I'll put galvanometer G2 over here. What's the direction of the current? It will be towards the left. And here also the nature will be the same in terms of the growth. So current will increase exponentially yeah, this part. So we are focused only till this part from 0 to P, and flux will also increase, yeah, the same logic, and of course the B will also increase. So overall we have I1 flowing from left to right, and then we have I2 flowing from right to left. How about the other part, when on the curve we talk about P to Q? So let's see all the parameters once again for both the cards. So current I, it will be a steady value. Yeah. So this time the graph, we have already reached the point P to Q. It will be, this is the nature of that current over time. Yeah. And that is for card 1. And B, magnetic field intensity, it would have also reached a maximum value, and it will follow the same pattern, similar pattern. And phi, which is proportional to B, will also follow the similar pattern. As far as the deflection in the galvanometer G1 is concerned, so it will be pointing to the maximum current, and of course it will be pointing towards right. But how about card 2? Will there be any current in the circuit? Now, since in card 1 we have there is no rate of change of flux. Flux is steady, so it is not changing. It has already achieved its maximum value, and it remains over there with respect to time. So in that case, there is no flux rate of change of flux in the secondary or in the card 2. Yeah. And therefore there will be no deflection. There will be, I can write over here, there will be a zero current over here, and there will be zero induced magnetic field on the card 2, solenoid 2, and there will be zero flux. Yeah. And as far as the deflection in the galvanometer is concerned, so it will go with what the value of the current is. So that since the current is zero, and therefore there will be no deflection, and therefore it will stay at the center point. Yeah. Vertically, it will point something like this, not leaning towards left and not leaning towards right. It will be at the center, indicating no current. To add one more point, since we have no current, so if I can put over here, as far as the poles are concerned, we still have north and south poles maintained in the card 1, but here in the card 2 there will be no poles because there is no current. Coming to the second part regarding the initial movement of the cards, so force on card 1 due to 2 will be equal to, in magnitude, to the force on card 2 due to card 1. Yeah. In terms of the direction, they will be opposite to each other, and magnitude is the same. So it is given that the mass of card 1 is twice the mass of card 2. Yeah. And before we go further, how do we get this, that the forces are equal? So if you see the force between two magnetic poles, it is proportional to directly proportional to the pole strength of the first pole and the pole strength of the second pole, and inversely proportional to the radial distance between the two. Please don't get confused over here. In this expression, M1 and M2 represent the pole strength. Based on this, we can conclude that F12 will be equal to F21 in magnitude. Yeah. So that's the background. Now coming back to our question, what will be the acceleration? So we know that force is equal to mass into acceleration, and therefore acceleration is equal to force divided by mass. So we have cart 1, cart 2. As far as the force experienced is concerned, it is the same magnitude F, and acceleration is equal to F divided by m1, and this is F divided by m2, and m1 is given as twice m2. So which one is bigger? So obviously, as you see, the acceleration experienced by the cart 2 will be twice the acceleration experienced by cart 1. So in a given amount of time, the cart 2 would have gone further distance, twice the distance away from C1, as C1 would have gone away from C2.